A new preprint from Florian Neukart at Leiden University demystifies the acceleration of interstellar comet 3I Atlas as natural outgassing driven by carbon monoxide and carbon dioxide jets. The models reproduce the comet's radial acceleration of 135 km per day squared and transverse acceleration of 60 km per day squared observed at its perihelion of 1.36 astronomical units. This explanation rules out requirements for radiation pressure effects or artificial propulsion systems. This changes everything. As of the 5th of November 2025, the preprint analyzes data from the comet's perihelion on the 15th of October 2025. Astrometric measurements from the Minor Planet Center, collected between September 20 and the 25th of October 2025, confirm the non-gravitational forces. NASA's Jet Propulsion Laboratory Horizon system processed these observations to quantify the acceleration components. That's the critical point. The immediate significance lies in how these models align the comet's behavior with known solar system comets. The simulated jets from less than 1% active surface area match the direction and magnitude of the forces. This confirms that conventional volatile sublimation accounts for the motion without invoking exotic mechanisms. Right now, scientists at Leiden University and NASA are validating the models against fresh post-perihelion data. Teams are cross-checking simulations with observations from the Hubble Space Telescope taken on the 31st of October 2025. I've been reviewing the preprint to assess its impact on prior anomaly claims. This is happening now. Current measurements from the 31st of October 2025 show the comet maintaining a stable trajectory post-perihelion. The radial component peaked at 135 km per day squared during the closest solar approach on the 15th of October 2025. Transverse effects reached 60 km per day squared based on positional residuals reduced by 80% when including outgassing terms. Scientists are paying attention. Instruments like the Atlas survey telescopes in Chile detected these shifts through differential astrometry. Data from the 10th of September 2025 onward captured the onset of acceleration as solar heating increased. The measurements integrate positions accurate to 0.1 arcseconds from ground-based observatories. Building on this, the quantitative breakdown reveals that mixed CO and CO2 compositions produce the required thrust. Sublimation rates at 1.36 AU yield gas velocities of 500 meters per second from active vents. For a nucleus radius of 1 kilometer, the mass loss equates to 10 kilograms per second during peak activity on the 15th of October 2025. The implications are significant. This data connects directly to the core question of whether the comet's sub-percent active fraction points to atypical ice composition after its estimated 10 billion year interstellar journey. Initial models suggest the low activity preserves volatiles from deep layers consistent with formation beyond the CO snow line in another stellar system. As of the 10th of November 2025, research teams led by Florian Neukart are running Monte Carlo simulations to test vent geometries. These incorporate rotation periods of 8 hours and obliquity angles from 0 to 90 degrees. NASA collaborators are feeding in Mars Reconnaissance Orbiter data from the 3rd of October 2025 flyby. Here's why that matters. In my analysis published on the 31st of October 2025, I had highlighted the acceleration as potentially anomalous. Neukart's preprint counters this by showing natural jets suffice with collimation factors of 2 to 3. The response prioritizes peer review submission by the 20th of November 2025. This relates directly to ongoing monitoring. The urgency stems from the comet's outbound path, where fading activity could mask further jets. Teams must capture data before brightness drops below 18th magnitude, in late November 2025. This window, closing by the 1st of December 2025, is essential for confirming model predictions. We're witnessing this in real time. Briefly, 3I Atlas was discovered on the 1st of July 2025 by the NASA-funded Atlas telescope, marking the third confirmed interstellar object. Unlike 1I Oumuamua, it shows cometary activity with a dust tail evident by the 21st of July 2025 Hubble images. Its hyperbolic orbit implies an origin outside our solar system, with a travel time of about 10 billion years. This leads to the present analysis. What differs now is the post-perihelion clarity. The 31st of October 2025 observations reveal no fragmentation, unlike some solar system comets at similar distances. The intact nucleus supports sustained outgassing, aligning with a low active fraction. Let that sink in. The primary theory under test involves anisotropic emission from 1 to 5 localized vents covering under 0.1% of the surface. Thermophysical equations balance solar input at 200 watts per square meter with sublimation energy of 2.7 times 10 to the 5th joules per kilogram for CO. As of the 12th of November 2025, iterations adjust for the nucleus density of 500 kilograms per cubic meter. This is not speculation. A competing explanation posits enhanced radiation pressure on asymmetric dust, but models show it underproduces the transverse component by 40%. The 30th of October 2025 report suggested propulsion-like effects, yet it lacks quantitative fits to the 60 kilometers per day squared value. The debate centers on volatile efficiency near 1 AU, where temperatures reach 180 Kelvin. CO dominates at these levels, while ammonia requires 150 Kelvin for comparable thrust. Neukart's simulations favor co-CO2 mixes by a factor of 5 inches, the acceleration match. Here's the key point. Latest evidence from ExoMars Trace Gas Orbiter spectra on the 3rd of October 2025 detects CO emission lines at 4.7 micrometers, supporting the mix. This tilts toward natural models with residuals below 0.05 astronomical units per day. Today, detections include a lengthening ion tail observed on the 8th of November 2025 by ground telescopes. The tail spans 0.5 degrees, indicating ongoing gas production at 5 kilograms per second. Patterns show diurnal variations in brightness tied to rotation and vent alignment. This is unprecedented. Measurements occur via the Hertz-Knudsen formula for flux, calibrated against Rosetta mission data from Comet 67P. Observatories like Pan-STARRS in Hawaii log positions nightly, with errors under 0.05 arcseconds as of the 14th of November 2025. NASA's Deep Space Network supplements with radar if feasible post-December. Adding to this, emerging patterns reveal thrust vectors shifting by 10 degrees over 24 hours, matching obliquity average models. The sub-percent active area persists, raising the core mystery. Does this low fraction signal atypical ice preservation from the 10 billion year trek? Scientists are actively investigating. This connects to whether diffusion-limited transport kept CO intact in shallow subsurface layers less than 1 meter deep. Preliminary fits indicate yes, with devolatilization minimal during solar system entry. The significance here is in ruling out exotics. Immediate next steps involve Hubble follow-up imaging scheduled for the 18th of November 2025 to map vent locations. Ground teams at Leiden are integrating these with Monte Carlo outputs by the 20th of November 2025. This week, James Webb Space Telescope observations on the 22nd of November 2025 will target infrared spectra for CO2 confirmation. As of the 15th of November 2025, the comet holds at a magnitude of 16.5, with acceleration effects diminishing to 20 kilometers per day squared outbound. Analysis confirms natural outgassing as the driver, per Neukart's preprint. The core mystery endures. The sub-percent active fraction likely reflects preserved ices from that interstellar path, but full composition awaits December data.